So I want to talk a bit about my presentation. We're going to talk about just what the overview is, what does the roll control system is, the electronic component, what the motivation behind having this electronic component to the system, and what the hardware decisions were. And I want to show you some of the prototypes that I'm working on and conclusions and future plans. So as he talked about the mechanical aspect of it, but the electronic system is usually it's just a sensor controlling, taking an angular velocity and outputting to taking an angular velocity and giving it to the microcontroller, and that microcontroller will deflect the servos that will adjust this roll to the desired speed. So just to visualize, here's a rocket showing how it'll spin, and the motivation behind using an electrical system is it's precise, it's automatic, and it's configurable. It's precise in the sense that if you say roll at 2 degrees per second, it'll start rolling at that rate. I mean, we have to calibrate it to do that, but it'll do it precisely. It's also automatic in the sense that there's no need for anybody to be there. If we start spinning the module, it'll detect the rotation and it'll adjust accordingly without any manual configuration. There's no like start or stop button. It's also configurable. Like Sam said, we can have it do different roll rates. So if the rocket size changes, if there's different weights, if anything changes, we can just program the microcontroller to adjust the different configuration. So when I first started, I'm a computer science major, so I don't know much about the hardware. So I started researching a lot of boards that are available in the market. But I chose the Arduino because of its ease of use. I saw a lot of TI, AT, all these little boards that require a lot of configuration. And as a computer scientist, I just like write code and expect some kind of output. But these boards are really hard to work with. The Arduino has an extensive community, which if I need help with anything, they can help me figure it out. And it's also very extensible. There's a lot of add-ons that you can add to it. It also has a great IDE, and IDE is the development platform where I can write the code and work with it. So, and for our project, this fit our needs. This is the sensor that we use to detect the rotation. It detects an angular velocity. The range is 50 degrees per second, which is good enough for what we're doing, because we don't expect it to be over and bigger than that. And we chose it to be one axis, since we're only focusing on the roll axis. So there's nothing else that we need to know. That will limit it makes it low cost, and we have less outputs. It's also okay. So that's the sensor, and the servo is just pretty much a standard servo. It's a high torque. It's very heavy duty, so it won't break very easily. It has to withstand a lot of the friction that goes on the air. And this is pretty much the prototyping as I have it in my desk. So I haven't put anything else. This is on the breadboard. This is all the wires. So once I got all the parts put together, like, all right, it starts launching rockets, right? Well, not really. With hardware, there's a lot of configuration that goes along. I didn't expect it to be this like a lot of work. So in computer science, just put in a value, you get out a result. But not in hardware. In hardware, you put in a value, and you get some like voltage back. But whatever that voltage is, I don't know. You have to read the specification, document. Well, after I read it, I thought it was going to be like a constant line. But no, I got this graph. I put the thing together, put it on my desk, and it started moving on its own. I wasn't moving anything, but it started moving. So it turned out that there's a lot of noise. This is over 500, this is like 500 samples, and it's all the noise that I got. So like you can see the very fluctuation, right? And it's not stable. So I looked up online, read a lot about filters. There's something called a Coleman filter. It's more of an electrical engineering, topic. But I did what I could and applied it to this microcontroller, and it cleaned out the signal so much. Just trying different constants. I went from being that noisy signal to this pretty constant signal. And to show you what it looks like, I hope this video works. So this is just on my desk, sitting, and I'll reset the controller, goes to a starting position, and I just move so it shows that it's working, right? Which is good, which is what I wanted. Before, I don't have a video of what it was doing before, but it was just jittering all over the place. So this is what it is, and our conclusion is just we want to show that this was possible with what we have. We have a microcontroller. We show that it can detect angular velocity. You can move to our desired rate, And our next steps are to attach this, to attach 2 more servos because our design uses 3 servos and put it and you do wind tunnel testing. So I conclude my presentation with this. Do you guys have any questions? Go ahead.
Was that filter you used in software? Is that
Yes, it's a software filter. So I wrote the code and it takes the input, applies it. It's called a Kalman filter, and it does its prediction. So it takes the next few points and it predicts like what it should be instead of what it actually is reading.
Interesting. One more thing. How long does it take for your computer to react to a change in the gyro?
Well, as you saw, it's very, very little changes. It seems to be a little bit of a lag, but it actually helps that it's a smooth transition rather than a sharp adjustment. So instead of